Hi, in this video I'm going to talk about what are the performance statistics that you can use in order to select the best classification model. Remember, we'll talk only about the classification model. So in the classification model you have models like decision tree, logistic regression, support vector machines, and so on. So we'll see what are the statistics available that you can actually use while evaluating your model and choose the one that actually suits you. Now remember, while you are classifying your data using a model, you can use multiple models. You can use decision tree, different types of decision trees. You can use logistic regressions and different types of logistic regressions, support vector machines, and so on, and compare the performances of the different models and select the one that actually performs the best. Okay, so what is the matrix that you can use? Okay, so you can use number of matrices. One of the important one that we can use is known as the receiver operating characteristics, or in short we call it as ROC. So its full form is receiver operating characteristics. All right. You can see in the right hand side, this is how the ROC curves looks like, and I'll explain what it means and how do you interpret the ROC curve. This basically originated from the signal detection theory, and it has now been heavily used by data miners, machine learning engineers, and economists. So it actually, what it shows is it shows the trade-off between the true positive rate and the false positive rate. So that's the trade-off. So what is the true positive rate and what is a false positive rate? That means a positive, something that you consider to be positive, or in your data it is considered to be is a 1. So for instance, is the event has come out to be event as part of prediction. So positive has come out to be positive, so that is the true positive. False positive is that something that is supposed to be a negative but has come out to be positive, so that is false positive. So for instance, a model has been built to detect cancer. Okay, now the model we have used, let's assume that we have used decision tree, and it gives us that somebody who has a cancer has been predicted to be cancer. So that is called true positive. Now we can have several such true positive cases where somebody actually having cancer is also predicted to be having cancer. But somebody actually having cancer, not having cancer. So somebody not having cancer, no cancer, is predicted to be cancer. Now that's called false positive, or in short known as FP. So we compare the actual versus the predicted. Okay, actual versus the predicted, and find the true positive and false positive, and then plot it, and the curve that you get for all the data points, you do that for your test data or training data, and you will the ROC curve. So in the right, in the y-axis you have the true positive rate, and in the x-axis you have the false positive rate. Okay, so ideally your ROC curve will always should be above the 45-degree line. So this is a 45-degree line, right? So this shows that this is the minimum prediction that your model should be able to do. So the ROC curve cannot be below the 45-degree line. So you can see. So this is the line that is 45-degree, right? This is 45-degree, or a straight line. Okay, so it cannot be below that. Okay, that's the minimum prediction that you expect from your model, right? Otherwise, the model is of no use if it is not able to give at least 50% good prediction, because if you toss a coin you would actually get 50%. So the model has to do better than that. Alright, so the ROC curve, so this is one ROC curve, this is one ROC curve. So the ROC curve should always lie between 0.5 to 1. Okay, so it always should lie between 0.5 to 1. The closer it is towards 1, it is a better model. Okay, so the more area it has under it, the better is the ROC, or the better is the model associated with that ROC. So there are two ROC curves here, right? One is this one, this area. So this is less compared to the second one, right? This is the second curve. We got the whole lot of this area as well. Okay, so the area under this ROC curve is known as the AUC, the area under curve. So that's give you sort of the the comparison matrix. So the one that is having higher AUC is the better model. So you can clearly see the second curve. If this is the first one and this is the second one, the second one is having better AUC, right? AUC is nothing but the area underneath this curve. Okay, the entire area you can consider for the second curve. Whereas for the first curve, this is the only area, right? So this is the first curve, right? Yeah. So AUC for second curve is better. So the model is better for the second curve. So that's the way you compare ROC. Alright, so another matrix that is often used is known as confusion matrix. It is often used in many areas, in medical science research, in credit scoring, in marketing, building marketing scorecard for targeting customers. So you use this in many prediction in many predictive models. And this is simpler to understand. You have the when you are building a classification algorithm, and let's, for instance, there are two class 0 and 1. Okay, or we could have class like yes and no. Okay, so you have an actual class and you also doing the predicted class, right? And normally what we do is that we take the probability value to be 0.5 as the threshold. So anything that is greater than probability of 0.5, so we consider that as an event, and let's, for instance, we are modeling for yes or 1, and anything less than that is no. Because remember, in a classification algorithm, it is always the probability that you get, right? So that's the way you classify. Okay, so you have actual class and you have predicted class. So, and just put it in a matrix. Okay, we have class yes. So this is predicted class, and the total number of actual class and predicted class matching cases is just considered to be A, and you can denote it as any number. Okay, it could be, say, for instance, there are 100 such total observations. Let's say 40 of them where the class is yes, actual class is yes, predicted class is also yes. So we have got 40% of that happening. The actual class is yes, but the predicted class is no, which is a wrong prediction, right? This is a wrong prediction. Let's, for instance, this is 20, so B is 20. And then actual class is yes, but, sorry, the actual class is no, but the predicted class is yes. So this quadrant, okay, third quadrant, for instance, let's say this is, 25%. So C is 25%. And the actual class is no and the predicted class is no. Again, that's a correct prediction, right? No has been predicted to be no. That is another 15%. So we will always want the model to be having high number of A and high number of D, because these two quadrants should be higher, because these are correct prediction. Yes to be yes, no to be no. Okay, the two opposite matrices, the diagonal, these two matrices with B and C, they are incorrect predictions, and you want that to be minimum. Okay, So this is one way of predicting your performance of your model or evaluating the performance of a model. So look at if the model is doing very good in calculating higher number of A plus D, higher number of, okay, how do I write? Okay, here I'll write A plus D, it should be high, and then B plus C should be low. Okay, just compare across models and find out which one is giving higher A plus D and which one is giving the lowest B plus C, and that's the one to be used for your prediction. All right. So another metrics that is used often is accuracy, and you can calculate accuracy from confusion matrix itself. So we have got A, B, C and D. We understood what these numbers are. When there is correct prediction, we have A and D. When there are wrong predictions, we have got B and C. And as I've already said, you always want A and D to be maximum. That percentage should be maximum. And the B and C percent should ideally be minimum for a model to be considered very good. Now you calculate accuracy by this A plus D divided by A plus B plus C plus D. That means the percentage of correct prediction. Okay, this is the total number, right? This is the total number of observations, and this is the correct prediction. A and D, remember, these are correct predictions, and this is the total number of observation data. So the percentage that you get a certain percentage, right? Accuracy always lies between 0 to 100%. Okay, in terms of percentage, in terms of fraction, it always lies between 0 to 1. Okay, the closer it towards 1, the better is the model. Okay, so that's the way you can compare the or evaluate the performance of a model and compare it with another model. There is a limitation of accuracy. So let's consider this is a two-class problem. That means we have got two classes, 1 and 0. Say for instance we have got the number of class 0 in the data set or in the example is 9,990, and the number of class 1 in the example is 10. So I've got very less number of 1 and more number or quite a lot of zeros in our data set. Now the predictive model has been built which predicts that all the data points are only zeros. All data points are 0. If that is the case, how do we find out the accuracy? Well, all the 9,990 zeros has been predicted correctly, and that will have a lot of weight in the numerator, right? In the formula, if you look at the formula, so this is correct prediction of no's, right, or zeros. So in this case we have got 9,009. So correct prediction, because the model has predicted that all the data points are 0. So it is incorrectly predicting the 10 once. So this is incorrectly predicting, but this is correct prediction for all the zeros. So in that case, you have 990 plus 0 in the numerator, because 9,990 is a correct prediction of 0, and there is just incorrect prediction of all 1. So your A is 0 and your D is 9,990, and the total number of cases is 10,000, right? Total number of observations is 10,000, and that comes out to be 99.9%. So accuracy is very good here. Accuracy is coming out to be 99.9% in this case, but the model is doing a very bad job. It is not able to predict even a single one. Even though the model is not able to predict single one, the accuracy is very good in this case. Why so? Because the percentage of 0 in the data set is quite high, and that's not a very good matrix to look out for or to consider in such case. So whenever you have a very less number of a very uneven distribution of 1 and 0 in a two class problem, it is always good not to use accuracy and just go using other matrices like ROC, Yeah, so these metrics, or maybe confusion metrics and other metrics that we'll be looking out in this particular session. So these are some of the important things you should remember while using accuracy. The next one is the cost matrix. Well, the cost matrix is similar to what you have seen in confusion matrix, except the fact that we are calculating the cost of missing out on a prediction, or the cost of a wrong prediction or right prediction. Wrong prediction and uh, and so this is wrong prediction and and correct prediction, right? Correct prediction and incorrect prediction. We can take an example and that would be better. Okay, so someone having cancer. Okay, someone having cancer. So model has been used to predict cancer. Someone group of probable cancer patients, and the prediction is that so someone actually having cancer. So this is actual and this is predicted, has been predicted to be not having cancer, and someone not having cancer but have been predicted to be having cancer. Okay, so what is the cost of wrong? So both the cases are wrong prediction. The first case is actual cancer, prediction is no cancer, whereas the second one is no cancer, actual is no cancer, but prediction is yes cancer, or there is cancer. So which one is more costly? Well, the first one is more costly, because if somebody is having cancer and is predicted to be not having cancer, then that will be a problem, because the patient without medication, somebody who is having cancer and not given medication, will die. Okay, so that is a very costly affair. Somebody who is not having cancer but having predicted to be having cancer will still survive, because he is not having cancer. Anyway, he is not having cancer, but there is a prediction. So over a period of time, this will be more clear, and he will be discharged from the hospital, and that is less costly. You can save the life. So the cost effect is more in this case. So not all wrong predictions or incorrect prediction has got same cost. So you cannot consider all the wrong predictions equally. It has to be dealt with different weight. What is called weighted. So instead of pure average, while calculating accuracy, we had just simple average, right? It should have been ideally it should have been weighted average with different weights to wrong predictions and correct predictions. Okay, so here is this example, computing cost of misclassification. So anyway, that's depend on one thing, that how you determine the cost of a misclassification. Okay, so here we have an example where the cost of misclassification for plus to be plus is -1 with some logic behind it, and minus to be minus is 0. So the correct prediction has a very less cost, whereas the wrong prediction has got higher cost. Okay, so the wrong prediction for positive to be negative, this is 100, and for negative to be positive is 1. And there are two models to it. Okay, model 1 and model 2. And we have got the cost, we have got the number of correct predictions and the wrong predictions for M1 and M2. By the way, the total number of observations is the same. It's just that the model has predicted differently. Okay, so here we have got 150, 250, 40 and 60. So we use this cost, so we just multiply 150 to -1 plus 40 to 100. So that's the way we calculate the total cost, and then 60 multiplied to 1, then 250 multiplied to 0, and the accuracy is 80%. Okay, you can calculate the accuracy, that is 150 plus 250 divided by 150 plus 40 plus 60 plus 250. Okay, that comes out to be 80%. and the cost is 3910. If you look at the model 2 and you calculate the accuracy, it comes out to be 90%, but the cost is higher. The cost is coming out to be 4255. Now your question is, which model should be used ideally? Well, going by the accuracy, you should say that model 2 is the better model because the accuracy is higher by 10%. So that is a clear answer. But the cost is more. And how important that cost is? It depends on the problem that we are solving. In medical science research, even a smaller cost, higher cost is actually very bad. And so it's important that we look for both the cases, the cost and the accuracy. So it entirely depends on the problem that we are dealing with. Alright, so one point. So wherever you have more importance for accuracy, you will always go for model 2 without worrying for the cost that you are incurring. But the cost, if cost is an important factor, then you always go for the less cost model, the model that incurs less cost, but accuracy would have to be compromised in that case. There are other measures known as cost sensitive measures. There is precision, which is calculated by this A by A plus C. So A is your true positives, and then A plus C is just, if you go back to the confusion matrix, so this is your matrix, right? A, B, C, D, right? Is that correct? Let me see first. So A, B, C, D, that's right. So this is your confusion matrix, and you can calculate precision as A by A plus C. You can calculate recall as A by A plus B. So these are two metrics that you can use other than what we have discussed. There is also F measure, which is given by 2A by 2A plus B plus. Then we have got weighted accuracy. Now we have discussed about, I was talking about the weighted accuracy that should have been the case, because we have seen the problem with the simple accuracy, right? So there are cases where you assign weights to different correct and incorrect prediction, and then calculate the weighted accuracy. Pretty much the way you calculate the weighted mean. Alright, so that's a better measure of evaluating model than the simple accuracy formula. There are more measures. You have already understood what true positive rate is, TPR rate or true positive rate. It's A by A plus B. We also known as sensitivity, then true negative rate. It's known as specificity. Now these two numbers have been used to measure ROC value. So if you're using ROC, you do not have to look into all these things. But sometimes, if you're really careful or really looking out for only the true positive rate, then this one is a better measure of accuracy of a model, or evaluating a model is better with TPR rate. In case we are very concerned or very focused on getting true positive rate, then there is false positive rate and false negative rate. So depending on the requirement of the problem that you're solving, you will use one of the metrics that that we have discussed so far. There is another way of measuring the prediction accuracy. Now this is more to do with a regression problem rather than a classification problem. Okay, so in a decision tree, support vector machines, or logistic regressions, so you only deal with classification of your data. But if you use a linear regression and decision tree for regression problem, then in that case you will you can use loss function in order to choose the best model, or the model that fits your data the best. There are a number of metrics that you can use. You can use absolute error. It's just the modulus of the difference of the actual minus actual minus predicted value, and then take the modulus of it, and then just sum it across, okay, across all the observation. That's absolute error. We've got square error. Just in case you want to square it, you just square it, so all the negatives and positive will become positive. So that's square error. And based on that, you can calculate different matrices. One is means absolute error, which is an industry used matrix to evaluate regression model performance. So that is just summation of your absolute error divided by the number of observations that you have. So this is mean absolute error, and then this is mean square error. So you replace your absolute value with the mean square, with the square error, and that's your mean square error. Is just summation across mean square and divided by the number of observations. Then we have got relative absolute error. So relative absolute error is the difference of in the numerator it's the same. The denominator, you just replace that with the numerator, except the fact that you are subtracting the mean from it. Okay, so that's the difference. Similarly with the mean square error. So this is a relative absolute error. That's another important matrix that is used to evaluate regression problems. So these are some of the matrix that you can use based on the problem that you are dealing with, based on the kind of model that you are using, and based on how important is a particular misclassification or a correct classification is for your problem. Thank you so much.